All right, so limits 5 is limits involving infinity. So there's two different types of limits that we're going to look at. We're going to look at limits that equal infinity and limits that as x goes to infinity. So we're going to look at both of those. First, we're going to look at limits that equal infinity. Both of these actually deal with asymptotes. So recall, a vertical asymptote makes the denominator 0 but not the numerator. So we find vertical asymptotes typically by setting the denominator equal to 0, but what makes the denominator 0 cannot also make the numerator 0 for it to be a vertical asymptote. So a lot of people skip over that part, but that's actually something that we'll talk about in section 6 with continuity. But that actually makes it a whole if it makes both 0, the denominator and numerator 0. Anyway, limits that are equal to a number over 0. So remember in section 3 I talked about there's 3 things that can happen when you plug a number into a limit. You could get a number, you could get 0 over 0, you could get a number over 0, and I said we aren't going to deal with the number over 0 right now. That's what we're dealing with today. So limits that are equal to a number over 0 are as x, I don't know what I wrote here. But as x goes to a vertical asymptote. So if you are taking the limit of as x goes to 5 of f of x and you get a number over 0, that means x equals 5 is a vertical asymptote. Okay, so that is that's what I'm trying to say here. I don't know what I was writing. Anyway. We often want to know which direction the vertical asymptote is going. Okay, so it has an asymptote. The limit doesn't exist in an asymptote. So technically, yes, you are correct by saying the limit does not exist for this. That's perfectly fine. You can always do that. However, sometimes, and on multiple choice, they will not give you both of these. Sometimes you want to know, is it going to positive infinity or is it going to negative infinity? It doesn't exist, but we want to know how it doesn't exist. We want to know which way it's going. Okay, so instead of saying the limit does not exist, we want to determine does it equal positive or negative infinity. So that is what we're doing with this. So for this first example, we want to take the limit as x goes to 5 with a little negative. Usually these will be one-sided limits. If they're not one-sided limits and you get a number over 0, you need to do both sides. So you need to change it to be one-sided limits, okay, because it's important to do that. You'll get different answers. So if we plug 5, even though you have the little minus there, you can still just plug 5 in. So if you plug 5 in, you get 12 over 0. Which is your cue to know, okay, this limit doesn't exist, but let's figure out, is it positive infinity or negative infinity? To figure out which one, you need to look at the superscript on the number. All right, so the little minus means less than 5. So what I do is, okay, I know it's equal to infinity. I'm going to plug in something just slightly less than 5 and see, is it positive or negative? So this is just to see the sign. So just to see the sign of infinity, I'm going to plug in 4.9, at least mentally, if not actually writing it down. So we're going to do 4.9 plus 7 over 4.9 minus 5. And hopefully it's easy to see in the numerator. I don't care what number it is. I just care about the sign. All right. You don't need to calculate this. You just need to know what the sign is. So like I said, you can do this mentally. So this is plus 4.9 minus 5 is going to be a minus. Positive divided by negative is negative infinity. So this limit is equal to negative infinity would be our answer. Okay. We know it's infinite because we got 12 over 0 at the beginning. We just wanted to figure out, is it positive or is it negative infinity? And to do that, you just plug in a number slightly less than 5 because we have that minus. If it was a plus, we'd plug in something slightly larger than 5. Like 5.1. Don't plug in 4 or 6 because that will sometimes give you wrong signs. Okay? You need to plug in something close to 5, but not 5. All right, so you're going to try this one on the Nearpod. So a couple more definitions. The limit as x goes to plus or minus, this is supposed to be a plus or minus infinity of f of x equals L, means that we can force f of x to be close to L by making x large or small if it's negative infinity enough. Okay, so by making x really, really large, we force the y values close to a particular value. So this is slightly different than the definition of an actual limit because the limit as x goes to plus or minus infinity is a little bit different. These limits actually find horizontal asymptotes, another type of asymptotes. The line y equals b is a horizontal asymptote if the limit as x goes to infinity equals b, or the limit as x goes to negative infinity equals b. You should have in pre-calc or maybe algebra 2 memorized little rules about how you know if there's a horizontal asymptote and what it is. This is where this comes from. All right, those rules come from doing limits as x goes to infinity and negative infinity. All right, that's just where they come from, but we can't teach them to you because you don't know limits yet in algebra 2 and pre-calc. Also, if you don't have a horizontal asymptote, those limits give you the end behavior of the function. So if they equal infinity or negative infinity, it's telling you what the end behavior of the function is. Algebraically, to find limits at plus or minus infinity, we divide by the largest power in the denominator. I'll show you that in the first example. However, there's a shortcut that you can take. You don't have to do that every time. You just consider the dominant part of the function in the numerator and the denominator. And this is kind of a big deal. You need to know that a number divided by infinity equals 0. Now, infinity is not a number. It's an idea that numbers get really big forever, okay, and never stop. So you need to think of, if you take 2 and you divide it by a million, it's a very small number. If you take 2 and divide it by a billion, it's an even smaller number. So as your denominator gets bigger and bigger and bigger, your division, when you do the division, it's going to go to 0. So we think of it as any number divided by infinity is 0. So that's important to know. Okay, so I'm going to do the algebraic version for this first limit. You can do it on the one that you're supposed to try as well. But then on the next example, I'm going to kind of take a shortcut. All right, so algebraically, you're going to look at your denominator and you're going to say, what's my biggest power? My biggest power is x to the 5th. All right, so I'm going to divide every single thing in my function by x to the 5th. So 2x to the 5th over x to the 5th plus x to the 4th over x to the 5th minus x squared over x to the 5th plus 1 over, why did I pick such a long function? And then 3x to the 5th. I know that denominator looks funny because I wrote it weird, but it's minus x squared over x to the 5th plus 5 over x to the 5th. I'm going to cancel, and yes, we have to write the limit every time. So this cancels and I get 2. This cancels and I get 1 over x. This cancels and I get 1 over x cubed. And then this is still 1 over x to the 5th. And then in the denominator I get 3. This is 1 over x cubed. And this is 5 over x to the 5th. And then if I plug infinity in, so again, it's awkward to talk about plugging in infinity because infinity is not a number, blah, 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 get over it. We're going to plug in infinity. So 1 over infinity, number over infinity is 0. All of these are going to be 0. All of these are going to be 0. We are left with 2/3. And there's no x to plug into, so it's just equal to 2/3. All right? So you're going to do that on this problem on Nearpod. Now, for this one, we're going to take a little bit of a shortcut. All right? We're not going to divide by the x cubed. Okay? You could, but we're not going to. What we are going to do is we're going to look at the numerator and look at the denominator, and we're going to say which would be the most dominant part of that function, of the numerator and the denominator separately. Okay, so if we look at 7x to the 5th minus x cubed, if x is a billion to the 5th is going to be so much larger than a billion cubed. I mean, I know a billion cubed is still really big, but a billion to the 5th is going to be so much larger that it's going to overpower this. So our function, as x gets really, in this case, really small, negative a billion to the 5th, that is going to be so much larger or smaller, since it's negative, than x cubed that the x cubed is going to be irrelevant. Okay, so we're going to boil that numerator down to 7x to the 5th. We're going to ignore the x cubed because it is going to be so much smaller than the x to the 5th, it's irrelevant. For this makes more sense maybe. If you plug negative a billion into x cubed, it's going to overpower, like that plus 1 is so insignificant, we could just drop it off. All right, it's not going to matter. This is going to be the thing that matters the most, the 3x cubed. You may not believe me with this, but just type in like a million to the 5th minus a million to the 3rd. It's going to be gigantic. All right, the million to the 5th is going to be so much bigger. So we can cancel this. We can simplify this. This is a simpler function. We can simplify it. It's 7x squared over 3. And then we can plug in negative infinity. Well, when you square a negative, it becomes positive. That works even with infinity. And it's 7/3 times infinity, basically. So this is infinite. Okay, anything times infinity is infinity. So that's infinite. So a little bit less algebra than doing this. You'd get the same answer. With this one, the square roots, you can do the same thing. The only tricky part is this negative infinity. And so I want to just do kind of the shortcut with this one, and then I'll explain why this one is a little bit different. So we're going to boil this down to the most dominant part of the numerator and the denominator. So the denominator, obviously the most dominant part is x. Okay, the minus 2 is irrelevant. When x is a billion minus 2 is still really large. Square root of 4x squared plus 1, same thing. This 4x squared is going to overpower the 1, even though we're inside the square root. But we do need to keep the square root on there. Okay, so you do need to keep the square root on the 4x squared. Now we can simplify. So after you do this boiling down to the highest powers or to the most dominant term, you can simplify. Square root of 4x squared is 2x. Then we can cancel our x's, and this is just equal to 2. Okay, so pretty simple. There's no x to plug infinity into. It's just equal to 2. Now the negative infinity, that's a little trickier. All right. The issue is that x is negative. Now, where this goes back to is when you're dividing by this highest power from the denominator. When you divide, if you were to actually do that, when you divide everything by x, you're going to take this whole square root by x. To get this x inside the square root and be able to divide it, you have to write it as the square root of x squared. But this is positive. This x, since x is going to negative infinity, this is actually negative. Even though we don't write negative x, since x is going to negative infinity, it would be negative. So we have to actually put this negative here. So what happens is when x is going to negative infinity, and this only happens with the square root, it's a special case. All right, it's a special case you have to kind of memorize, really. Only happens with the square root. When you do this whole boiling down thing, you have to add a negative to it. So you have to do negative 4x squared or 4x squared over x. And then you do your whole thing and you get negative 2. Okay, so that is only because that's negative infinity. And only with a square root. Okay. And then you're going to go ahead and try this one. I gave you a hint. Look at the graph of e to the x to find these two. Okay.